Welcome to the lecture series in computer science. We are seeing a series of lectures in the subject problem solving and Python programming. In today's session, we will be seeing a topic on algorithmic problem solving. The contents of the session are, we will be saying about the purpose of algorithmic problem solving, and then we will see how to understand a particular problem. As well, we will see the designing and analyzing the algorithm. We will as well see the strategies for developing an efficient algorithm. What is an algorithmic problem solving? An algorithmic problem solving is a technique of solving the problem that requires the formulation of an algorithm for a solution. You have a particular problem. So, how do you solve that particular problem? How you are going to formulate it? That is what you are going to see. So, that is what the algorithm definition states. The algorithm problem solving is a technique of solving the problem that requires the formulation of an algorithm for the solution. Let us now see how the algorithm was designed and how the analysis is taken place. So, here in this diagrammatic representation, first of all you are supposed to understand the given problem. So, understanding is mandatory. How you are going to understand makes a difference. So, if you are going to understand it correctly, you will be in a position to represent it well. Then after you understand the problem, because first of all you have a problem, you know it is a problem, you do not know how to solve that problem. So, in order to solve the problem, you need to have a better understanding. So, when you understand the problem, you then decide on the computational means. After deciding the computational means, what do you mean by computational mean? How you are going to do the computations. So, after deciding the computation means, we will be giving the exact versus approximate algorithmic problem solving. Sometimes we will have an exact solution, or at times we have an approximate solution for problem solving, and then we have the algorithmic design technique. So, this is said to be a flow graph. After understanding the problem, you decide on the computational measures, you do exact solving, or at times you get an approximate solving, and then you have an algorithm design techniques. Then based on the computational means and based on the exact solving means that we have received, we move over here for the design of an algorithm. So, here in this step we design the algorithm, and when we design the algorithm, we should be doubly cautious in designing, and then we need to check whatever we have designed, whether have we designed it correctly, whether any issues are there. So, we are supposed to check it out. So, when we are checking it, we are supposed to prove the correctness of the design. So, we are supposed to prove the correctness of the algorithm. So, whether the logic that you have used, whether the logic is correct, whether we are able to correct the algorithm. So, the logic, the design has to be proved for correctness. Then we analyze the algorithm. Here we analyze what does the algorithm is, how efficient the algorithm is, whether the algorithm is efficient. See, anyone for that matter can write the algorithm, but whatever algorithm that you write, it should be efficient, it should be effective. So, we are supposed to analyze the algorithm, and then we are supposed to write the program code for the algorithm. Then based on whatever we do here, after you analyze the algorithm, supposing if there is any issue during analysis, then what happens is that as we again move on over here to decide on the computational means. So, here again we move on to decide on the computational means. Then after making the decision, If it is correct, again we design the algorithm. Again we do the redesign work. Supposing if we get, when we are going to analyze the algorithm, when there are any flaws during analysis, we go to the design part, we do check for the computational means, check for the exact solution, exact solving technique or the approximate solving technique, and then based on this we again redesign the algorithm as far as the analysis is concerned. When you are going to design an algorithm and when you are checking for correctness of this algorithm, at this step itself, if you have an issue, then we again move to the backward step and we here itself we decide on the computational means. We do exact and approximate solving, and then based on this algorithm design technique we design this algorithm. So here itself, when you come to know that your algorithm that you have designed is not proved to be correct, is not perfect, then you decide and you go back to the computational means and you check the exact solving means or you check the approximate solving means for algorithm design technique, and then you come to the designing of an algorithm proving its correctness. Here itself 80% of the algorithm will become correct, and then when you analyze, when you find the problem, you go back, when there is an issue then you go back to the design and you carry out the design work. If you have analyzed the algorithm, the logic of the program correctly, then you start coding the algorithm. So this will be the end part as far as the algorithm designing, algorithm problem solving is concerned. So I repeat, first of all you are supposed to understand the problem, then you are supposed to decide on the computational means, you are supposed to have the exact and approximate solving, then you are supposed to find out the exact technique for the algorithm design, you are supposed to find out a technique, based on the findings you are supposed to design an algorithm. If the design is correct, you are supposed to check for the correctness, you are supposed to validate the algorithm by proving the correctness, and then if you find that it is not, the design of algorithm is not correct, you go back again, you decide on computational means, you decide on a different design technique and you design the algorithm. If it is correct, then you go down, then the correctness of the algorithm, you analyze the algorithm. Here only you check the effectiveness and efficiency of the algorithm. So analysis of algorithm is done in this phase. Then if the analysis is correct, you do the coding part of the algorithm, or else if it is found to be wrong, if you think it is not so effective, then you go back to the previous position and again you start computing, you start with the computational means, you find out the exact and approximate solving technique, and then you try to find out the exact algorithm design technique that is to be used, and then you start the designing of an algorithm, then you prove the correctness, then again you analyze the algorithm. If the algorithm is analyzed, then the coding part, the algorithm has been coded. So this is how the algorithm design and analysis process takes place. Now let us find out what is to be understood in the problem. How am I going to understand the problem? Understanding the problem, it is the process of finding the input of the problem that the algorithm solves. It is very important to specify exactly the set of inputs the algorithm needs to handle. A correct algorithm is not one that works most of the time, but this correct algorithm or an approximately correct algorithm is that it works correctly for all sort of legitimate inputs. How do you give the inputs? The input are given in terms of data. The plural of data is data, the singular of data is datum. So, you feed the inputs. Based on the input that has been fed, you can check the working of the algorithm. You can check the correctness in terms of working of an algorithm. So, this is how you understand the problem. Then after understanding the problem, what you are supposed to do? You are supposed to ascertain the capabilities of the computational device, and you are supposed to choose the exact problem solving technique for this algorithm, for identifying this algorithm. So, how are you going to ascertain the capabilities of a computational device? What do you mean by the computational device? As far as the computational device is concerned, here you are going to state what is the variable that you are going to use, how you are going to do the computation part, how it is being computed. So, that is what you are going to check, and you are going to choose the exact problem solving technique in order to solve the problem. Now, let us see how we are going to do it. If the instructions are executed one after the other, then it is called as line by line execution, or it is as well called as sequential execution, sequential algorithm. Such an algorithm you call it as a sequential algorithm. If the instructions are executed one after other, it is called sequential algorithm. Then if the instructions are executed concurrently, simultaneously, at the same instance of time, if two or more instructions are being executed, then such algorithm you call it as a parallel algorithm. Based on this, the algorithms are classified as exact algorithm and approximate algorithm. Any instruction, when it is being fed line by line, when it gets executed one after the other, it is called sequential algorithm. Any algorithm, any instruction which gets executed concurrently at the same instance of time, parallelly at the same instance of time, then such an algorithm you call it as a parallel algorithm. Then based on this, you can classify the algorithm as whether it an exact algorithm or whether it is an approximate algorithm. So, with this you can compute the capabilities of, you can ascertain the capabilities of the computational device, as well you can be in a position to choose the exact problem solving technique. Then next is about deciding the data structure and methods for specifying an algorithm. Now, how do you decide a data structure? So, what is a data structure? A data that has been in a structured form. So, a data structure plays a vital role in designing and in analysis of the algorithms. Some of the algorithms design techniques, and those techniques, it depends on structuring the data, specifying a problem's instance. Here the structured data, it has been given in such a way that it specifies problem instance. What is a program? A program is a summation of algorithm and data structure. You call it as a program. Let us see methods of specifying an algorithm. How an algorithm is specified? Algorithm is specified by two means, either in terms of writing a pseudocode or in terms of drawing a flowchart. Now, so these are the methods of specifying an algorithm. So, writing the pseudocode and drawing the flowchart which we have seen in the previous session. So, we will see in this session we will be saying we will be checking how the algorithm is said to be correct. We will prove that correctness of algorithm. So, once the algorithm is specified, the correctness has to be proved. A common technique for proving the correctness is to use mathematical induction, because an algorithm's iterations provide a natural sequence of steps needed for such proofs. So, here again you require sequential execution of steps. So, you require a natural sequence of steps for checking such proofs. Tracing the algorithm's performance for a few specific inputs can be very worthwhile activity. It cannot prove the algorithm's correctness conclusively, that is, you can prove the algorithm, working of the algorithm only to an extent, but as a conclusion you cannot say this is the best algorithm to solve this particular problem. In the very near future you may get an algorithm which may also be equally best or which may be even more better than the existing algorithm. So, as of this moment you can say this algorithm is said to be working correctly, it is said to be efficient, but you cannot prove that algorithm's correctness conclusively. That is what has been stated. Then next is, let us see how to analyze the algorithm. Any algorithm is analyzed by two means. One is in terms of its efficiency, second one is in terms of its simplicity. So, how has an algorithm been analyzed effectively and efficiently? That in terms, when it is going to be analyzed efficiently, it is again classified into two types. One is with the help of time efficiency, second one is with the help of space efficiency. As far as the time efficiency is concerned, it indicates how fast the algorithm runs. The execution of the algorithm matters a lot. Say for example, for the same set of program, if you are going to have 2 or 3 different algorithms and the execution of the first algorithm takes 2 nanoseconds, the execution of the second algorithm takes 4 nanoseconds, the execution of third algorithm takes 3 nanoseconds. Which algorithm was said to be time efficient? The algorithm which took 2 nanoseconds for executing is said to be an effective algorithm. So, as far as efficiency is concerned, as far as the time efficiency is concerned, whatever algorithm that takes least time duration is said to be an effective and an efficient algorithm. So, a time efficient algorithm is one that determines how fast the algorithm will take its time for execution or will take its time for running a particular task, particular logic. Then next is about the space efficiency. We have seen the time efficiency with respect to how fast the algorithm runs. Now comes the space efficiency. In terms of space efficiency, it indicates how much extra money or how much extra memory it uses. Space efficiency, by the term space, what can you infer? It is how much of space it is going to occupy for its execution, how much of memory space it is going to occupy for its execution, how much of extra additional memory space it is going to occupy for its execution. That is determined with the help of space efficiency. Again I repeat, the efficiency is classified in two types. One is time efficiency, Other one is space efficiency. Time efficiency denotes how fast your algorithm runs, how quick your algorithm gets executed. Space efficiency denotes how much extra memory it takes for its execution. Then next is about the simplicity. As far as the simplicity is concerned, what do you mean by simplicity? When you are going to code, when you are going to have an algorithm, it should be simple enough, it should be crisp, but it should be sturdy. Sturdy in the sense it should be so efficient in terms of execution. An algorithm should be precisely defined and investigated with mathematical expressions. An algorithm, if it is defined with mathematical expression and if it has been placed to the point, then you claim such an algorithm to be so simple. Simplicity. Then the other point in terms of simplicity is simpler algorithms are easier to understand and are easier to program. When you are going to have an algorithm, when you are going to write an algorithm, it should be easily understandable. It should not be so tough. When you read the algorithm, the logic, you should be in a position to understand. When you are in a position to understand only, you can write the equivalent codes, you can write the set of codes. When you are going to write the set of codes only, it becomes easy to program. Then the next simplicity is the simple algorithms. It may be simple, but I said it should be sturdy, it should be effective, it should be efficient. Whatever algorithm that you write, it should be simple, sturdy, effective and efficient. When you are going to write an algorithm in such a format, then such algorithms will contain fewer bugs. What is that fewer bug? Bug is an error, wherein if you have an error, it will not be executing properly. So you are supposed to create an algorithm, analyze an algorithm in such a means that it has fewer bugs, and the algorithm that you create should be simple, should be efficient, should run as fast as possible, should consume less time duration in terms of execution, should also take into consideration of the space efficiency. It should not take much of memory space when it is executing. So if it is not going to take much of memory, when it is faster, when it is simple enough, then this algorithm will be one of the best, it will be a better algorithm. So this is how you analyze the algorithm. Then we come to we will see how to code an algorithm. As far as coding an algorithm is concerned, we have now formulated the algorithm by understanding the problem. After understanding the problem, we have designed what we are going to take for the computational means, how we are going to take into consideration the computational devices, and then how we are going to design an algorithm. Then we have designed an algorithm, we have checked for the correctness of an algorithm, and then we have analyzed the algorithm. After analyzing the algorithm, we are supposed to go in for coding of an algorithm. When you are going to do the coding of an algorithm, most of the algorithms are destined to be ultimately implemented as computer programs. Coding is nothing but writing computer programs, writing it into different languages, using of languages such as C, C++, high level languages such as C, C++, Java, Python, so on and so forth. Programming an algorithm presents both a peril and an opportunity. A working program provides an additional opportunity in allowing an empirical analysis of the underlying algorithm. So any program, any algorithm when you take and when you start writing your code, it should be in a workable format, it should be working, and when you execute it, for you may think the program is executing, the program is running, you are getting an output, but internally the logic matters, internally the algorithm matters, internally when you get a faster execution, it is not based on the programming, it is not based on the program that you executed, it is based on the algorithm that is available, it is based on the effectiveness and the efficiency of the algorithm that is available. Then such an analysis is based on timing of the program, on several inputs, and then analyzing the results obtained. When you start coding your algorithm that you have analyzed, you are supposed to see to that how fast your algorithm executes, how minimum the space, the memory space that it takes into account. So these, and as well how simple your algorithm is. These three things you are supposed to take into consideration when you analyze, and based on the analysis, based on the effective analysis, you do the coding part, and when you code it, you have a faster execution. Now let us see the strategies of developing an algorithm. It is classified into two types, one is iteration and recursion. Iteration, it is a sequence of statements that is executed until a specified condition is true, is called iteration. For example, the for loop and the while loop. What is recursion? A function that calls itself is called recursion. A recursion is a process by which a function calls itself repeatedly until some specified condition has been satisfied. So these are some of the strategies for developing an algorithm. Now let us summarize this session. We have seen the purpose of having the algorithmic problem solving. We have seen how to understand a particular problem. We have seen how to design and analyze a problem. We have as well seen the strategies for developing an efficient algorithm by using an iterative approach or by using a recursive approach. Thank you.